Welcome everybody to AP Physics presented by Alan Su. Today we'll be going over pressure. So imagine you have a 1 by 1 square here and a force is applied on it. Well, you could say this force is applying pressure on the square. Pressure is defined as the force divided by the area it is being acted on. The standard unit of pressure is a Pascal, PA, and since the unit of force is a Newton and the unit of area in our case is meter squared. A Pascal is just a simplification of newtons per meter squared. So another common unit found in life is pounds per square inch, PSI. We usually see that in tires and balls. 1 kilopascal, denoted by its prefix kilo, is 1,000 pascals, and the atmospheric pressure at sea level is 101,325 pascals, or simplified is 101.3 kilopascals. Atmospheric pressure is the pressure applied by gases in the atmosphere at sea level. We'll go further into this later. So since pressure equals the force divided by the area it's acted upon, as the force increases, pressure will increase. And since the area is in the denominator, as the area increases, the pressure will decrease. So going back to our original example, with this 100 Newton force and 1 by 1 square, since pressure is force divided by area, we could see that the pressure applied on the square is 100 newtons divided by 1 meter squared, which is 100 newtons per meter squared. So this means the force is applying 100 pascals of pressure on the surface. In a separate example, we have a 50 Newton force being applied onto a 2 by 2 square. So same equation, pressure equals force divided by area. We have this pressure equals this 50 Newton force this time, divided by 2 by 2. So we have 12.5 newtons per meter squared as the pressure. So this force is applying 12.5 pascals of pressure on this 2 by 2 surface. So what is atmospheric pressure? Atmospheric pressure refers to the force exerted by the air molecules in Earth's atmosphere on surfaces within it. It decreases with altitude due to the decreasing density of air, and standard atmospheric pressure at sea level is around 101.3 kilopascals, which I have already said. So atmospheric pressure. So as we go up in altitude, there's less and less air molecules above us that's acting a force on us. And since pressure is force divided by area, if there's less molecules above us acting a weight force down on us, that means there's less pressure from the atmosphere as we go further up in altitude. And so that means as we go further up in altitude, the atmospheric pressure will be less than 101.3 kilopascals. So atmospheric pressure influences weather patterns and are measured with barometers, and the pressure is vital in aviation and meteorology. So now there are two types of measurements of pressure that we will use. The first one is gauge pressure. Gauge pressure is pressure relative to the local atmospheric pressure. So this means simpler is how much more or less pressure than the atmospheric pressure there is. So, for example, at sea level, there's 101.3 kilopascals of pressure. The gauge pressure will measure the difference of the pressure starting at the atmospheric pressure. So for example, we have this tub of water here with a Mr. Thrasher, a depth h below the surface. And we have the atmosphere in the air above it. So since gauge pressure is pressure relative to the atmosphere, we're counting the atmosphere as our starting point, or 0. So in this case, the gauge pressure is just the pressure of water acting on Mr. Thrasher. So since we know that gauge pressure is the force divided by area, and looking at this, we know that the only force acting on Mr. Thrasher here is the downward force of the water above him. So it's the weight of the water above him. So we could replace F by mg, and we could create this other equation, mg over a, which is mass of the water times the acceleration due to gravity. Also, with our physics equations, we know that density is equal to the mass divided by the volume of an object. We're using this subscript density so we don't get P confused with pressure. And with this equation, we see that m can also be equal to the density times the volume of an object. Plugging this into our gauge pressure equation, we have gauge pressure is equal to the density times the volume times acceleration due to gravity divided by area. Now, to find V, we know that in a cylinder here, or any object here, you have an area of a base and the height. And so we know that the volume is equal to the base times the height. But in our case, we'll use B equals A because it's this area of the base. So plugging this value in V value into our equation up here, gauge pressure equals density times acceleration due to gravity times AH divided by A. And simplifying down, we have gauge pressure equals to the density times H times G. So this is our gauge pressure equation, density PHG. So in our example here, the gauge pressure acting on Mr. Thrasher is the density of the water above him times the depth he is at, H, times acceleration due to gravity. The second measurement of pressure is absolute pressure, denoted by PABS. Absolute pressure has the absolute zero as its reference, or zero pressure. And absolute pressure, because of this, it is the total pressure present in a situation, counting both the local atmospheric pressure and the gauge pressure. We're still going to be using atmospheric pressure at sea level, but it doesn't really matter. So at sea level, absolute pressure equals gauge pressure plus 101,325 pascals. So at the sea level, the absolute pressure is the equation we derived earlier, PHG plus 101,325 pascals. Thank you for listening. Use a quick meme. Thank you for listening. I'll see you guys in the next one.